All right. Welcome, welcome. My name is Edvard Hübinette. I do protocol architecture for DeSci Labs. This presentation is going to be a bit about how we choose to implement our underlying data infrastructure for the open protocol that powers our applications. So specifically, we're going to talk a little bit how we can solve scientific publishing problems with IPFS. So what we're doing is we're building tools for a radically transparent scientific record, and we build web apps to help researchers create persistent research publications. In the long run, we want to make sure that we can safekeep and navigate the collective human knowledge. And I'm not going to focus too much on our product in this talk, but rather kind of what DAG structures we need to be able to express for any of this to work. So we're going to see how we use IPFS and IPLD to publish, organize, find, and interact with scientific data. And to give you some context about what I'm kind of going on about, I'll quickly show you kind of how the application looks so you get like some context. So what we have here is the web portal that the researcher will use. So they will upload their paper, their data sets, their code, and this is the way to kind of see that. So to the left, you have basically a Google Drive style file tree. In the middle, you have like the front matter of the paper, and then you have like attestations and the activity log. So basically the versions of the publication that the author has created. So let's look at some background, like how this is currently built, and later I will kind of show how we are going to like transform it in the next generation of the protocol. So at the base, we have something that we call the research object, which is kind of what we just looked at in the front end. This is represented as a manifest file around the Unix FS DAG root. So the content of the publication is what you see in the tree. So you have like a directory called data, which has a SQL database and some CSV data, and you have a docs directory. To add context to this, because just these files doesn't say much about the scientific publication that it kind of represents. So to accompany that, we have a manifest file, which has an IPLD link to this tree. This holds the like science context for it. So like the title of the paper, information about the author, which research fields it's a part of, the contributors, which license it's under, and et cetera, et cetera. But there's an issue here. What if the author wants to update this and add a code directory to this file tree? Because as we know, like this would change the CID of the data structure and hence also the CID of the manifest file. So how do we keep track of this? How do we like solve the versioning problem? The way we do this is we bind the manifest CID to a unique key in a smart contract map. So basically you mint a little like access token, which gives you control over, let's say, the key 45 in a mapping. This allows you to like authenticate yourself for updating the linked manifest file. So when you do that, we emit an event, and through tracking these events, we can build up the history of how this publication has changed over time. So this hits like almost home. There are some issues with it still. Like this works, we use it. That's kind of what we have deployed right now. But there's a single data type, and that is the research object. We want to be able to like track contributions of many different kinds, so we need more data types to keep track of. And it's also the issue that a single author controls all of the context for the publication. So if all the metadata, for example, about the content of the research object is in this manifest file, which means that only the original author of the paper can update the metadata. There is also no like natively linked history in the IPLD sense, because we like implicitly compile it from the events from the updates on chain. There is also the requirement of a smart contract transaction every time the author needs to update a publication, which is quite a big UX hurdle, because for the space that we work in, the traditional scientific or academic community have a very low tolerance for crypto balances and seeing tokens and managing gas and stuff like that. So these are basically the issues that we kind of need to solve with the next iteration. So we have needed to rethink the underlying data layer on how we're going to represent the content here. So I've worked on defining a protocol for a collaborative open data graph to be able to represent all of these publications and the scientific context around it. So I'll take you through the abstract DAG requirements that we need to express this data and how we ended up building it. So as a first naive idea, if we don't want to track them on chain, can we just toss them onto IPFS? There is a IPLD structure called DAG Jose, which would be a way to kind of take the manifest file and then sign that whole bundle of data with the private key of the author. So doing this, if you looked up two different DAG Jose objects, you would see that they are signed by the same author, so we could reach verified authorship. However, these don't share an identifier. So these are two loose points floating around in space. There is no relationship between these. There's also no historical lineage. So figuring out which one came first, what is the newest version. And we can't just put a link to the previous one, because then when you create the third version, you could just also create new objects to kind of replace the history. So we have no way of actually knowing whether or not the history has changed without kind of trying to find all of these and trying to map out what's the truth. There is also no way to discover these as they happen. So the author publishes an update. How would I know? That's really tricky, because IPFS doesn't give us the tools to do that. So from this, we kind of realize we need a way to chain these updates together into some structure. So we've implemented this with Ceramic, because what it gives us is a way to represent append-only versioning under a shared identifier. If you know about IPNS, or the Interplanetary Name Service, naming scheme, where you can have a mutable pointer that points to content addressable storage blobs, but with a versioned history. So basically seeing where did it point before this and where does it point now. And this is what Ceramic does. So all additions to the history need to be signed by the original DAG to be accepted by the network. We get an umbrella PID, which is A here, identifying this entire chain of updates. We also get the historical lineage as a stream of commits, because the network won't let you add a commit if it doesn't build on the same history that the network knows the stream state to be. Through this, we can resolve anything. So we can resolve a specific, that CSV file in version 0 there. We can go identify the stream, find that specific commit, and then slash our way through the UnixFS file structure to find that particular file at that specific version. And this is exactly what we need to track the version history. However, we still have one key issue, which is how can we resolve and discover new instances of research objects? Given a single research object, we can find all of the updates, but how would we find a completely new one? How would we find B in this case? So we need a way to find data instances from the schemas that they implement, and this is what ComposeDB adds to Ceramic. So we create a schema for what we consider to be a research object, and then we can query ComposeDB gives us a DAG of instances following the schema that we can query to find all of the data. So we can discover instances made by the model regardless of where and when it was created or by whom. So all of this information is accessible over IPFS, but we get a contextual DAG over the relationships between them and the models they implement. So we forgot kind of about one thing. So the original manifest file that contained a lot of different types of metadata. So like about the author, the research fields that it was part of, annotations, metadata. So we've kind of lost track of that. We could add them into the model. So like put them as schema entries in the research object, or we can just keep them in the manifest. So the way we've kind of split this together, split it apart, is to create models for the different types of contributions you can do to build up a more complex graph or more expressive graph of how entities in this data layer kind of relate to one another. So with subcomponents, you can have more granular contributions. And like this diagram shows you like a user profile. You can see 2D IDs have their own profile, implementing the profile model. And through ComposeDB, we can find these instances. You can see that both DIDs have created their own research publication. So like RO there stands for research object, which implement another model. You can also see that DID2 here has assigned a attestation by creating that model, and it includes a reference to a specific version of the research object that the Professor Fig has created. So like everything here is granularly creditable, versionable, verifiable, and automatically discoverable without having to rely on any like central party. We can do relations in this through using these persistent identifiers. So either we can reference the stream itself, which basically would resolve to the latest state, so like the latest update by the author, or we can refer to a specific commit, so like a specific state at a point in time, if you want to have it like deterministically resolvable, which is exactly what you want if you want to do a reference to a particular scientific paper, for example. So another thing that's really cool about this is how it's extensible by the community. So each of these models are independently indexed, which means that the community can create extensions of the protocol. So they can create a new data type and create new types of references, which can be found by everyone participating and like being interested in finding this data. So for example, let's say someone starts to encode publications with semantic embeddings, basically allowing you to like chat with an LLM to like learn about the content of a publication. Someone can create a model for this, which they instantiate and add the embeddings from a particular paper and use a reference to point to that paper. Anyone who is interested in having these embeddings can start indexing this model and enjoy this new type of context that's suddenly available. And this is without any type of like governance. There doesn't need to be like a central decision like in a DAO. Anyone can just like create this model, start using references to this research object, and just like add a completely new type of context. In the same way, let's say the data layer kind of evolves. We want like a new way to represent something. It's the same there. You can just add that, and they can coexist. We can support both, and you can practically deprecate, as in like stop creating new content with the old model, but they can coexist. There needs to be no like formal upgrade decisions or anything like that. So we talked a little bit about context around the publication, like the research field, for example. That's something that's not unbounded. Like you usually have like a couple of research fields. But metadata in the scientific community is like a bit weird. And there are 3 magic words for being compliant with all of these like open science standards. And that is metadata format agnostic. If you are not metadata format agnostic, like you basically don't have anything in the eyes of the kind of open science metadata community. So this makes it quite hard to put in the models directly on the network, so we need to like link it in. Like the reason for this whole thing is to ensure that the publications and their metadata is forward compatible for like machine actionability and basically any type of information that could in the future be useful to have associated with a publication, like retroactively. This means that we can put no practical limit on either the size nor the format or shape of the metadata. So we can link them in. So like the manifest file at the root of the publication could have a link to a CID, which would hold like a whole bunch of metadata. But we want the participation. We want people to be able to granularly contribute with metadata. So this is one example of how we can do this. I made this figure really, really big because I thought the screen was going to be small. But now we have a huge diagram. So basically, an author can add context to a raw DAG node within the file tree that's associated with a research publication. We use something called a research component model to do this, where you can add some information. So like here, they tagged it as like flight data. You can also like use some useful for like curing or useful for discovery stuff in the component itself. But then you can add like the bulk of the information as a link to a CID to a JSON file containing basically an unbounded amount of arbitrary metadata. The community can kind of extend this and suggest corrections or additions by creating an annotation targeting this component and linking in a JSON patch. It doesn't necessarily need to be JSON. We can call it like, any patchable, serializable data if that feels better. So this works, but there is like a canonical metadata file, which like it's kind of the truth, and then you have like a bunch of suggestion. Me personally, I think it would be very satisfactory if we could just see this as like a sea of metadata shards. This is another way to do it. So like basically removing the difference between an author's own definition of what is like the metadata for a publication and putting it at the same level as the rest of the community that can contribute metadata. This means we can like remove the metadata king and just kind of have a floating sea of information around it. So how this would work is that the original author can, again, like tag the nodes of the DAG with JSON like CRDTs. So this is conflict-free replicated data types, which is basically a way of representing, it's kind of what underpins stuff like Notion and Google Drive. So like you can have concurrent edits and it's kind of guaranteed to converge to the same state. So by doing this, you could like compile the metadata after some arbitrary filtering or selection. So let's see, like what is the metadata if we compile all of the contributions from just the author? And what is the metadata as provided by other community members on the same research object? Or we can filter it and like, I just want the metadata from authors active, like that have published paper within the biotech community, for example. So this will allow you to like very granularly select what you think is the important like subset of metadata for a given situation. This is extremely powerful. There is like no way of managing metadata for scientific publications that can do these types of things. I realize I went through this a lot faster than I had planned, but that just means that we have plenty of time for questions. I'll just mention that this like open data layer protocol type thing is what we call the DeSci Codex, which we unveiled last week. You can find the documentation on that to the link up to the left. Check it out, hit me up. I would love to discuss this stuff. And I hope this was interesting and or fun. And I want to thank you for your time. Got some questions, perhaps?
Hi. So you presented us a version that, from what I understand, is the previous version of this system, where you used IPFS or IPLD and a smart contract, correct? And then you moved to a new version where you have the IPFS, IPLD layer, and you use ceramic. The way I see it, maybe I'm wrong, is that the new version of the new model does not provide the same level of assurances as the previous model. I mean, if I had to bet who will be longer around, because we're talking about scientific papers and scientific information, and I had to bet for a blockchain or ceramic, I would bet for the blockchain. Nothing against ceramic, I think it's a great tool. So what's your take on this?
Yeah, that's a very good question. The fact is that all of the content that ceramic manages is stored on IPFS, so it's accessible through IPFS. So it's basically just a way of kind of managing how it gets created and how it's linked together. But the storage, like the underlying storage assumptions and the linking assumptions are the same. So with ceramic, we get what they call stream IDs and commit IDs to find these things. Like, as long as someone pins this data, you can still find the same relations. But for short URLs, which are kind of important in this field, we're still going to use a smart contract to give short identifiers and connect those to the identifiers for the ceramic streams. Mm-hmm. There are a couple of reasons for this, but honestly, mainly it's because short URLs is an important design requirement for this field. Okay. But we can do an important change, because the smart contracts in the original version, that requires the author to have publication access to be able to update their own key in the contract. What's cool about this is that they can just create a stream where the commits will be the updates. So we have one identifier that's never going to change for the publication, which means that we can trustlessly relay to anyone else to create this entry in the smart contract for you. So basically, if you do it through our platform, for example, we will just register you for the short URL. We can do that, and we can't trick you in any way. Either it points to your CID or it doesn't. So it still allows us to completely remove the need for the end user to interact with the smart contract. Okay. And we get the same kind of findability properties.
Thank you.
What type of researchers are the early adopters that you've observed so far?
We do have some. So one is a prominent planetary science researcher at NASA. We have one very famous geneticist who has been. It's been a very good use case because that field has a lot of large data sets that they have a lot of issues sharing with each other. So for example, the genetics data set has been generated over millions of hours on a supercompute cluster and contains 135 terabytes of genome sequences. And that's locked behind a very low egress bandwidth line on a university data center. So basically just saying I want to have this data. If you manage to have the disk space, which is unlikely, it takes you 380 days to get it out. These aren't time frames that are that fun to work with. So by storing it on something that's compatible with content addressability, you can also use stuff like compute over data networks, like Bacalhau and a bunch of similar technologies, to basically, instead of getting the data to run your code over it, you would just send the code and run that over the data where it's being stored. And this is, this solves a lot of problems for these researchers. So yeah, we're basically initially targeting researchers in a wide variety of research fields, where the common denominator is that they have a large dependence on big data sets, and they have issues sharing it with the community. And yeah, communities where data sharing is important.
Any other clusters of researchers that you're looking at now? As in within that area, anything also specific that you're now kind of outreaching actively to?
I didn't really catch that.
So in that area of, you said that there's a particular, almost like a prototype, like they have big data and they need to run analysis. Are there any other, like are you doing active outreach to them somehow?
Yeah. So the focus now is kind of what we call white glove onboarding. So basically showing scientists that are prominent in their respective fields how to use this and offering help to them to like convert their paper and build up a reproducible representation of it using this stack.
All right, cool, thanks. Yeah.
All righty. Thank you so much for your time.